So far, we've covered Layer 2 and Layer 3 addressing and discussed how data is routed through a network. Now let's dive into the details of IP addressing. Earlier you learned that every network interface has a Layer 2 or MAC address and a Layer 3 address. You learned that an Ethernet MAC address is assigned by the manufacturer of the NIC, providing no way to logically group devices. At the same time, a Layer 3 address is a unique identifier assigned by a network administrator as a way of logically grouping devices. Each Layer 3 address has two portions, a network number and a host number. As we saw already, routers use Layer 3 addresses and routing tables to transmit data between networks. But it's not enough that the data have a Layer 3 address. Transmitting data between networks requires a common Layer 3 protocol. While there are others, the most common Layer 3 protocol is the Internet Protocol, also known as IP, and IP Layer 3 addresses are known as, not surprisingly, IP addresses. The Internet Protocol uses these addresses to transmit data from a source network device to a destination network device. IP also performs other services, such as fragmentation and reassembly of data or datagrams for transmission over networks with different maximum data unit sizes. We'll cover these functions in more detail later in this section. To understand how IP works, it helps to cover a little history. In the 1960s, the Advanced Research Projects Agency, or ARPA, part of the U.S. Department of Defense, started to build a wide area computer network to connect important research organizations. The goal of this network, known as Arpanet, was to share expensive or scarce computing resources. This network initially connected only 4 computers. More locations were connected over time. Arpanet was the first true network of mainframe computers and was the predecessor of the Internet. LANs, as we know them, were a concept that was years away. As time went on, other wide area computer networks were built, but each used a different technology. It became obvious that to communicate between these networks, a new standard protocol would be needed. That new standard protocol became the Internet Protocol, which was developed in the early 1970s. IP has evolved over time. Most people today are familiar with IP addresses that look like the examples on screen. These addresses are IP version 4, or IPv4, which is used by most home and business networks. Unfortunately, the pool of available IPv4 IP addresses has almost been exhausted. As a result, an increasing number of research and educational facilities, service provider, and corporate lab networks are using the next generation protocol, IP version 6, or IPv6. The major difference between the two is the size of the address. IPv6 addresses are much larger, 4 times larger than IPv4 addresses, in fact. The larger address size means we won't exhaust the supply of addresses for many years to come. Because most people are more familiar with IPv4 addresses, though, that's where we'll focus our attention. When a computer needs to send data, the Internet layer adds an IP header to the data to form an IP packet, also known as an IP datagram. We've been showing a simplified version of the IP header, but it actually includes many fields. Let's take a moment to look at all of the fields in the IP header. On screen, you can see all of the fields in the IP header. Notice that the source and destination IP addresses are just 2 of the fields in the header, and they actually appear near the end of the header. Move your mouse over each field to learn more about its function. When you are ready to move on, click Continue. each device in an IP-based network must have a unique IP address. As we've mentioned before, a Layer 3 address has two parts: a network portion, commonly referred to as the network prefix, and a host portion. The network prefix is also known as the network number. In the simplified format we've been using, it's easy to see which part of the address is the network portion and which part is the host portion. Now let's replace our simplified addresses with standard IPv4 addresses. The format shown on screen is known as dotted decimal notation. Looking at these IP addresses, it isn't as easy to determine the network portion and host portion of the address. Now at a glance, you might look at the IP addresses in Network 1 and assume that the first three numbers, 192.168.1, indicate that network's number, and looking at Network 2, the numbers 192.168.2 indicate the second network's number. In this particular example, that assumption would be correct, but as we'll soon see, IP addresses are more complex than they might appear at first. Consider the example shown on screen now. All of the IP addresses in both networks begin with 192.168.1. How does the router know which addresses are in which network? To understand how routers work, you have to understand that they don't see addresses the same way we do. In fact, the dotted decimal format we've been using was created just to make it easier for people to work with addresses. Routers use addresses in binary format, which is actually their native format. Each number in the dotted decimal format represents an 8-bit binary number. Each 1 and 0 is a single bit, so an IP address is actually a 32-bit number that is separated into 4 groups of 8 bits each. Don't worry if you don't understand binary numbers. We'll explain them in detail in just a moment. Some of the bits in an IP address are used for the network prefix, and the remaining bits are used for the host portion. The challenge is that the number of bits used in the network prefix is not a fixed value. The network prefix might take up most of the 32 bits, or the host portion might, or they might divide the bits equally. Because an IP address does not clearly indicate which bits are network bits and which bits are host bits, every IP address has a corresponding 32-bit network mask. Also known as address masks, subnet masks, and simply net masks, network masks are used to identify the network portion of the address. Network administrators assign a network mask to each interface on each device, just like they do IP addresses and default gateways. If you launch a command prompt on your PC and type ipconfig, you'll see the mask configured for your computer. The IP address and network mask together identify which bits are used for the network prefix and which bits are used for the host portion. In a mask, if a bit is turned on, in other words, if it's a 1, the corresponding bit in the IP address is used for the network prefix. If a bit is turned off, or a 0, in the network mask, the corresponding bit in the IP address is used for the host portion. So, in the example on screen, the first 24 bits of the address are the network portion because the corresponding mask bits are turned on. Now in this example, the first 27 bits are the network portion for the same reason. But before we start discussing the details of IP addressing and network masks, we need a math lesson on how to convert binary numbers into decimal numbers and back again. As we mentioned, IP addresses consist of 32 bits, each of which can either be a 0 or a 1. If we tried to use these bits as one big chunk, it would be very difficult to manage and understand. For simplicity and clarity, we break the 32-bit address into 4 groups of 8 bits each. Each group of 8 bits is also known as a byte, or an octet. As we mentioned, to help humans work with IP addresses, each octet is converted into a decimal number. In this section, we'll take a look at how to convert the binary number shown on screen into a decimal number in dotted decimal notation. When humans deal with numbers, we use the decimal number system, also known as the base 10 system. This system uses 10 digits, 0 through 9, that can be grouped together to form a decimal number. Each position within a decimal number represents a power of 10. The table on screen shows places for the first 4 powers of 10. 10 to the third power is 1000, or the thousands place. 10 to the second power, or 10 squared, is the hundreds place. 10 to the first power is the tens place. And finally, 10 raised to the 0 power is the ones place. Remember that any number raised to the 0 power is always 1. Now let's look at an example. The decimal number 3,407 can easily be broken down into the different powers of 10 shown on screen. If you do the math for each position in the decimal number, you can see how we come to 3,407. While the decimal system is a base 10 system, the binary number system is a base 2 system. This system uses only 2 digits, 0 and 1. In the binary number system, each position represents a power of 2, as shown on screen. In this table, we show places for the first 8 powers of 2, which is equivalent to 1 octet of an IP address. Because any number raised to the 0 power is 1, 2 raised to the 0 power is still the ones place. The next bit position is 2 raised to the first power, or the twos place. Next is 2 raised to the second power, or the fours place. This scheme continues all the way up to 2 raised to the 7th power, or the 128th place. In a binary number, each digit is 1 bit, so the table on screen could hold 8 bits. Let's look at an example. We'll start with the first octet of the 32-bit IP address and determine its decimal equivalent. On screen, you'll see each position represented with the correct power of 2. Remember that when we look at decimal representations of numbers, a 1 in the hundreds place means one group of 100. A 1 in the tens place means one group of 10, and so on. In binary representation, a 1 in the 128th place means one group of 128. A 1 in the 64's place means one group of 64, and so on. Here you see that only the 128th place and the 64's place are turned on, because these bits are set to a 1. All others are turned off or set to a 0. By adding 128 and 64, we discover that 192 is the decimal equivalent of the binary number. Now let's determine the decimal equivalent of the second octet. Following the same procedure, we determine which bits are turned on, calculate their decimal equivalent values based on the powers of 2, and add these numbers together. Here, the 128th place, 32's place, and the 8's place are all turned on. Adding these 3 values together, the decimal equivalent of this binary number is 168. Now it's your turn. You need to determine the decimal equivalent of the third octet. Calculate the decimal equivalent of the binary number on screen and type it into the table. When you are finished, click Check Answer. Now you need to determine the decimal equivalent of the fourth and last octet. Calculate the decimal equivalent of the binary number on screen and type it into the table. When you are finished, click Check Answer. Not quite. Try again. Here is the full binary to dotted decimal conversion of our 32-bit IP address. What is the greatest possible number that can be represented in one binary octet? If we set all 8 bits to 1, the decimal equivalent is 255. So, with 8 bits, you can only represent decimal numbers in the range of 0 to 255. Now that you know how to convert an 8-bit binary number into its decimal equivalent, let's reverse the process and convert a decimal number to an 8-bit binary number. In this example, we will convert the IP address 207.17.137.229. To convert from decimal to binary, starting from the leftmost digit, check whether that power of 2 position fits into your decimal number. In the example on screen, we first ask, does 128 fit into 207? 128 fits into 207 one time, so we set that bit to a 1. We then subtract 128 from 207 and see that we have a remainder of 79. You might be asking yourself, because binary numbers can only be represented with ones and zeros, what happens if the number fits into that place more than one time? Remember that with 8 bits, the decimal number can never be larger than 255, and 128 only fits into 255 one time. Using the remainder of 79, we consider the next lower power of 2. Can 64 fit into 79? Because 64 fits, we set that bit to a 1 also, and then subtract 64 from 79. The new remainder is 15. Moving to the next column, we see that 32 does not fit into 15, so we set that bit to 0 and the remainder is still 15. We also see that 16 doesn't fit into 15. We set that bit to 0 also, and the remainder is still 15. Continuing along, can 8 fit into 15? Yes, so we'll set the 8-bit to a 1 and subtract 8 from 15. The new remainder is 7. By now you can see how the process works. Let's complete the conversion. Can 4 fit into 7? Yes, so we set the 4's place to a 1 and subtract 4 from 7. The remainder is now 3. Can 2 fit into 3? Yes, so we set the 2's place to a 1 and subtract 2 from 3. The remainder is now 1. Can 1 fit into 1? Yes, so we set the 1's place to a 1. Subtracting 1 from 1, we have a remainder of 0, and we've successfully converted the decimal number 207 into the binary equivalent shown on screen. To verify our work, we can convert binary back to decimal by adding up the powers of 2 that are turned on. It should add up to 207. Now let's convert the second octet, 17, into a binary number. We quickly determine that 128, 64, and 32 do not fit into 17, so we set each bit to 0. Moving on to the next column, 16 does fit into 17, so we set the 16-bit to a 1. Because we have a remainder of 1, the 8, 4, and 2 bits are set to 0, and the 1 bit is set to 1. To verify our work, we add up the powers of 2 that are turned on and see that it equals 17. Now it's your turn. You need to determine the binary equivalent of the third octet. Start from the left side of the table and enter a 1 or 0 depending on whether the power of 2's place can fit within the decimal number. If it does, subtract that power of 2 and find the remainder. Proceed from left to right as we have demonstrated. When you have the answer, click Check Answer. Now you'll determine the binary equivalent of the fourth and last octet. Use the table on screen to calculate the binary equivalent of 229. When you have the answer, click Check Answer. Here is the full dotted decimal IP address converted into its binary equivalent. We just learned how to convert a binary number into its decimal equivalent and a decimal number into its binary equivalent using IPv4 addresses. Earlier, we mentioned the hexadecimal number system, which MAC and IPv6 addresses both use. Click the link on screen if you'd like to learn more about hexadecimal numbers. When you're ready to move on, click Continue. Now that we know how to convert binary numbers to decimal numbers and vice versa, we'll examine how a device determines its network number. But first, why does a device even need to know its network number? Earlier we learned that each broadcast domain is assigned a unique network number, and each device within a broadcast domain is assigned a unique host number. We also learned that devices in the same broadcast domain have the same network number and can communicate directly without the help of a router. Devices in different broadcast domains, however, have different network numbers and need a router to communicate. Until now, we've been using the simple Layer 3 addressing scheme of network number.host number, so it's easy to tell if a device is in the same network or not. But now we're going to start using IP addresses, so it might not be as easy to tell whether a device is on the same network. Take a look at the example on screen. How does a device, whether PC or router, know if it has the same network number as the device it's trying to communicate with? Each device already knows its own IP address, of course. But remember, that information is not sufficient for determining the network number. To determine the network number, also referred to as a network prefix, a device uses its network mask. Here you'll notice that the network mask is 255.255.255.0. Like IP addresses, masks are also 32 bits long and can be represented either in binary format or in dotted decimal format as shown here. 255.255.255.0 is the decimal equivalent of all of the bits in the first 3 octets being set to 1. The bits that are turned on in the network mask designate the part of the address that is the network number. Now that we know how binary numbers work, we can see how network masks work in detail. Each bit of the mask has one corresponding bit in the IP address. As we mentioned previously, the network mask has a 1 in every bit position used for the network number and a 0 in every bit used for the host number. When a device needs to determine its network number, it compares each bit in its IP address with each bit in its network mask. If both bits are a 1, the device sets the corresponding network bit to a 1. If either bit is a 0, the device sets the corresponding network bit to a 0. The network portion of the address is exactly the same as the IP address, and the host portion of the network number is always 0. As you can see, the result is the binary equivalent of the device's network number. Like IP addresses and network masks, though, the network number is usually represented in decimal form, as shown on screen. Note that representing the network mask in decimal form can cause confusion because the network mask is not actually an address. The introduction of classless interdomain routing, or Cider, helped alleviate this confusion somewhat. With Cider Notation, also known as slash notation, the address is still shown using dotted decimal format, but it's followed by a / and the number of bits used in the network prefix. The number after the slash is also known as the prefix length. In the example shown on screen, the bits in the first 3 octets are all turned on, meaning that the first 24 bits are network prefix bits. So 192.168.1.8/24 means that the first 24 bits are the network prefix and the last 8 bits are host bits. We can also use Cider notation to identify a range of addresses. So 192.168.1.0/24 identifies the address range starting at 192.168.1.0 through 192.168.1.255. Now you might be thinking this all seems pretty obvious, and in this case you are right. The first 3 octets of the IP address, represented in decimal fashion, are 192.168.1. And because the prefix length is 24, the first three octets of the network number must also be 192.168.1. When the network mask falls on an octet boundary, such as a prefix length of 8, 16, or 24 bits, determining the network number is fairly straightforward. But it's a little harder to determine the network number when the network doesn't fall on an octet boundary. Originally, IP network numbers always fell on an octet boundary. With the advent of Cider, network prefixes could be any length and often don't fall on an octet boundary. The older system of routing was called classful routing. Cider, if you remember, stands for classless interdomain routing. To learn more about classful and classless routing and the problems Cider helped solve, click the link on screen, or click the Continue button to continue with this topic. In just a few moments, we'll take a look at how you can determine a network number when a network mask does not fall on an octet boundary. But first, let's finish with our example. Our network is shown on screen, now using Cider notation to indicate the prefix length for each network. What happens when PC 192.168.1.8 wants to send data to 192.168.1.3? First, it puts the destination IP address and source IP address, but not the mask, in the packet. Next, it uses its network mask to determine if the destination IP address is on the same network. If its IP address and the destination IP address have the same network number, which is the case here, it can send the data directly to that address. After the PC determines the destination PC's MAC address using ARP, it encapsulates the packet into a frame and sends the data to the destination. Let's take a look at another example. Here, the same PC wants to send data to 192.168.2.20. Once again, the sending PC applies the configured network mask to the destination IP address. This time, however, the network number is not the same. Because the PCs are not on the same network, the PC sends the data to the default gateway for further processing. Devices use network masks to determine their network prefix. But a network mask also identifies the valid host numbers on a given network. In any network, the first address, where all host bits are set to 0, identifies the network number. The last address, where all host bits are set to 1, is always reserved as the broadcast address for the network. You might remember that a broadcast address is an IP address that allows information to be sent to all devices on a given network. All numbers except these two reserved numbers are valid host numbers. In the example on screen, 192.168.1.0 is the network number. The broadcast address is 192.168.1.255. Therefore, host addresses in this network can lie in the range that begins with 192.168.1.1 and goes up to 192.168.1.254. If you know the prefix length of a network, you can easily calculate how many individual host addresses are available on the network. The formula to calculate the number of hosts is 2 to the power of the number of the host bits, minus 2. You subtract 2 because the network number and broadcast address are reserved. In a /24 network, there are 24 network bits. That leaves 8 host bits. Using the formula, we calculate that we have 254 host addresses available for our network. If more host addresses are needed or more network numbers are needed, we'd have to change the size of the network mask, which we'll cover next. Let's quickly recap some of the concepts we've learned with an example. When we last visited the Acme company, they were growing their network, expanding into several buildings on a single campus. Now they've decided to build a new manufacturing facility in a different area of the country. Let's say that you're the network manager at the new location, and you're in the process of developing your IP addressing scheme. You have been assigned the address range of 192.168.3.0/24. This Cider notation, also known as the Cider block, represents the address range 192.168.3.0 through 192.168.3.255. So you can use IP addresses for hosts starting at 192.168.3.1 and ending with 192.168.3.254. With the current 24-bit mask, you have one network, 192.168.3.0, with 254 hosts. Now suppose you determined that you need at least 5 networks or separate broadcast domains, each requiring a unique network number. Each network will have no more than 25 hosts. How are you going to take this single IP address range and break it into smaller networks? The answer? IP subnetting. IP subnetting means taking a single network number and splitting it into smaller networks or subnets, which is short for subnetworks. You create a subnet by changing the mask assigned to each broadcast domain. Said another way, you extend the size of the mask, creating more network numbers with fewer hosts per network. The original address range used the first 24 bits for the network portion of the address, leaving 8 bits for the host portion. To create a subnet, you adjust how many of the 8 bits will be network bits and how many will be host bits. More network bits means fewer hosts per network. More host bits means more hosts with fewer networks. It's a balancing act. Move the slider on the interactive visual on screen to see how changing the size of the mask impacts the number of networks and hosts possible in each network. When you are ready to move on, click Continue. You might have noticed in this interaction that you could only move the slider within the last octet of the address range. Once you've been assigned a specific network range, you can only make the network prefix length longer, not shorter, because other networks will also be using the first 24 bits. Now let's take a look at how you would actually calculate the number of networks and number of hosts within a network. Let's use our power of 2's table again to help us complete the calculation. First, we'll divide the 8 bits of the last octet in half, allocating 4 bits for network bits and 4 bits for host bits. Using 4 bits for network bits allows for 2 to the 4th, or 16 different networks. That's each binary number between 0000 through 1111. Using 4 bits for the host bits allows for 14 different hosts. Remember that we always subtract 2 from the number of possible hosts because there are 2 reserved addresses. In the scenario we presented at the start of this section, you need at least 5 networks with 25 hosts each. With a network with a prefix length of 28 bits as shown on screen, you wouldn't have enough hosts per network to meet your goal. Is it possible to meet that goal by allocating 3 bits of the last octet for network bits and 5 bits for host bits? Complete the calculations below and fill in the blanks with the number of networks and hosts per network possible. When you are ready, click Check Answer to continue. Not quite. Try again. That's still not correct. Here are the correct answers. On the network side, with 3 bits, we have a total of 8 different network numbers, which meets our requirement of 5 unique network numbers. With 5 bits, we can now support 30 hosts per network. Perfect! So Acme's networks at the new location will use a prefix length of 27 bits. To determine the decimal equivalent subnet mask, we simply add up the bits that are turned on in the last octet. The total is 224. On screen, you see the full subnet mask that will be used by each network at your location, with a prefix length of 27. Now, let's go back to the question we asked earlier. What happens when a network prefix doesn't fall on an octet boundary? We saw that when a network prefix falls on an octet boundary, it is very easy to determine the network portion and the host portion of the address without looking at the binary equivalent. Here you can see that the first 3 octets represent the network number, and the last octet represents the host address. Remember also that the first number in a subnet is reserved. In this example, it's easy to see that the IP addresses ending in 0 are the reserved subnet numbers, and those ending in numbers other than 0 are hosts. Here are the addresses of the first subnet and first host in that subnet, shown in binary and decimal format. When a single octet comprises both network and host bits, however, it's not so easy to tell the difference between a network number and a host address. You have to look at the binary equivalent. Notice here that with a 27-bit prefix length, the first available subnet number is actually 192.168.3.0, where all bits in the subnet portion are turned off, and the first host address in this subnet is 192.168.3.1. Nothing looks different yet, but let's keep going. The second available subnet is 192.168.3.32, where the far right bit in the subnet portion is turned on. The powers of 2 table on screen shows you how the bits in the last octet now add up to 32. The first host address in this subnet, then, is 192.168.3.33. Now this address, or host address, looks very different, and here is where the purpose of the mask really becomes clear. If the network prefix does not fall on an octet boundary, it is impossible to determine the actual subnet number without the mask. Using the subnet mask and converting binary to decimal, we can start to build a table of the network numbers available and the host ranges possible within each network. The table on screen shows the first 2 subnets we just looked at, displaying both the dotted decimal equivalents of the full IP addresses and the last octet of the binary numbers. Now let's say that PC 192.168.3.60 wants to communicate with 192.168.3.66. Do they need a router to communicate? Once again, the first step is to determine if the 2 devices are on the same network, or, in this case, the same subnet. We apply the subnet mask to the source IP address and determine that the subnet number is 192.168.3.32. Now if we apply the same subnet mask to the destination IP address, we determine that the subnet number is 192.168.3.64. Because the 2 devices are not on the same network, they must use a router to communicate. Remember that Acme's manufacturing facility was assigned the network range of 192.168.3.0/24, which they needed to subnet to meet their needs. The table on screen shows each subnet number and the range of assignable host numbers in decimal using a 27-bit subnet mask. The table also shows the last octet in binary of each subnet, as well as its corresponding host address range. Remember that there are 2 reserved addresses in each subnet. Now let's assign a few of these subnets and see what the new IP addressing scheme looks like at the Acme manufacturing facility. In the graphic on screen, you'll see that we've assigned 3 subnets, 192.168.3.0, 192.168.3.32, and 192.168.3.64 to the 3 different networks. We've also assigned 3 host numbers from each subnet to the network devices within each subnet. Notice that the router has 3 network interfaces in 3 different subnets, so it must have a unique IP address for each. Now you try it. In this exercise, let's say you've been assigned an address range of 192.168.10.0/24, but you want to subnet your network to meet your business need. Your goal is to create 4 different networks with at least 50 hosts per network. First, decide what prefix length should be used for your networks. How many bits of the last octet should you use for the subnet portion of the address and for the host portion? Move the slider to indicate your answer. Then click Check Answer. If you'd like a hint, click the hint link. Not quite. Try again. That's still incorrect. Designating 2 bits for the subnet portion will allow for 4 networks. The 6 bits remaining for the host portion will allow for up to 62 hosts per network. Now, how would you represent the subnet mask you have indicated using dotted decimal notation? Type your answer in the spaces on screen. Then click Check Answer. If you'd like a hint, click the hint link. At this point, you might be asking yourself, how does a company go about getting an IP network address? From the very early days of the Internet, IP network address assignment was centrally controlled to ensure that no two networks would ever try to use the same IP network address. In the early 1980s, John Postel, an Internet pioneer, voluntarily maintained a list of assigned network addresses, supposedly in a paper notebook. The Internet Assigned Numbers Authority, or IANA, was established to centrally manage the global. Postel administered addresses for IANA for years and allocated addresses to any organization or company that filled out a simple request. As the Internet expanded across the world and addresses started to become depleted, it quickly became clear that one central organization could not administer all addresses. In the early 1990s, 3 regional Internet registries, or RIRs, were formed to work with the IANA and administer IP address allocation regionally. As time went on, 2 additional RIRs were added. Finally, in 1998, Internet Corporation for Assigned Names and Numbers, or ICANN, was formed to be responsible for all IP address assignment and domain name registration. This nonprofit public benefit corporation assumed control of IANA and now coordinates the allocation and assignment of IP addresses and domain names. ICANN allocates IPv4 and IPv6 address blocks in a hierarchical manner to the 5 RIRs. These RIRs then allocate blocks of addresses to national Internet registries and local Internet registries. Internet Service Providers, or ISPs, depending on their size and reach, obtain their address space from one of these registries. Companies or organizations obtain their IP addresses from their ISPs. Some IP addresses are reserved for specific uses. For example, the private IP address ranges shown on screen can be used within a company's network but cannot be used on the Internet. Companies are free to use IP addresses out of the private address space within their internal network, which is also known as an intranet, a term you're probably familiar with. Companies must not use these networks outside their intranet because these same private addresses are used by many other companies as well as home networks. A network host, such as a PC or a workstation, has a loopback interface, which is a virtual software interface not associated with or connected to any hardware that a device uses to send a message back to itself. It is commonly used for troubleshooting and network testing. The IP address 127.0.0.1 is used as the loopback interface's IP address. A loopback interface has several uses. A PC can communicate with a local server without an actual network connection, so it's useful for testing services without exposing them to the security risks of accessing them through the network. A device, such as a PC, might have a web server running on it. The same PC might want to communicate with the web server directly. In this case, the PC uses its loopback address in the URL to communicate with the local web server. Multicast IP addresses are similar to multicast MAC addresses, something we discussed earlier in the course. Like multicast MAC addresses, devices use multicast IP addresses to send the same data to a specific group of devices. Routing protocols, streaming media services, and Internet television, or IPTV, often use IP multicasting. Now that we understand IP addressing and subnet masking, let's combine this knowledge with the material we learned earlier in the course. Examine the network map on screen. It should look very familiar. We have simply replaced the simple network number .host number addresses with actual IP addresses. Notice that we're using IP addresses from a private address space. For simplicity, we'll continue to use the abbreviated MAC addresses. So let's use our new understanding and see what happens when PC 192.168.1.2 wants to send data to 192.168.1.8. We'll zoom in on the first network to get a better look at what's happening. First, the PC needs to know if the destination address is on the same network. It uses the network's prefix length to determine its own network number and the network number for the destination address. In this case, they're on the same network, so the two PCs can communicate directly without the help of a router, which is also known as direct routing. Because the PCs are on the same network, the sending PC needs to determine the destination PC's MAC address. So it sends out an Address Resolution Protocol, or ARP request, to every device on the same network. Notice that the router does not forward Layer 2 broadcast frames. Only the device with the requested IP address replies with its MAC address using Layer 2 unicast addresses. Now the two PCs can communicate directly. A router wasn't even involved in the process. Now let's see how data flows from a PC on one network to a PC on a different network. In this example, PC 192.168.1.2 wants to send data to PC 192.168.3.2. Again, we'll start by zooming in on the first network. Once again, the PC must first determine if the destination PC is on the same network by using its network mask to extract the network number from the destination IP address. This time, the two PCs are on different networks, so a router is needed to forward the data along to the final destination. This process is known as indirect routing. Instead of sending the data directly to its final destination, the PC encapsulates the packet in a frame addressed to its default gateway. If the PC doesn't know the router's MAC address, it sends out an ARP request. Once it learns the router's MAC address, it sends the data to the router for further processing. As we saw previously, the switch uses a MAC address table to forward data. However, because our main focus is on IP addressing and routers in this section, we won't show the details of switch forwarding anymore. When the router receives the frame, it first examines the destination MAC address. If it is the router's MAC address, the router strips off the Layer 2 frame and looks at the destination IP address. It then looks in its routing table to find a network matching this destination IP address. Earlier, we learned that routers use routing tables to determine the best path to a destination network and forward packets toward that destination. The routing table contains all destination network numbers known to the router and how to reach them. Note that in this network, the router only keeps track of network numbers, not individual host addresses. Routers use static routes and dynamic routing protocols such as the Open Shortest Path First, or OSPF protocol, or the Intermediate System to Intermediate System, or ISIS protocol, to learn about remote networks and build their routing tables. The details of these protocols are beyond the scope of this course. Each entry in the routing table includes the destination network number and prefix length, the next hop along the way to the destination network, and which port or interface on the router should be used to reach the next hop. The next hop either indicates that the destination network is directly connected to the router or provides the IP address of another router on a directly connected network. When a router receives a packet, the router uses the routing table to make intelligent decisions on where to send the packet next. While it isn't shown in the example currently on screen, in many cases, a destination IP address might match multiple entries in the routing table, each with a different prefix length. When that situation occurs, routers always look for the best match for the destination IP address. The best match is the match with the longest prefix length because it is the route with the most bits matching. We'll look at longest match routing in more detail in the next section. Here's a chance for you to perform some of the actions of a router. First, find the best match for this packet's destination IP address in the routing table. Click the row in the table that best matches the destination IP address. Now the router needs to add a new Layer 2 frame, including the next hop router's MAC address. Complete the source and destination Layer 2 addresses in the frame shown on screen. Then click Send Frame. Use the Send ARP Request option if needed to get information to complete the frame. It then forwards the frame out the designated port. The next router repeats the strip and lookup process, looking for the longest match. Once again, click the row in the routing table that best matches the destination IP address. Complete the source and destination layer 2 addresses in the frame shown on screen. Then click Send Frame. Use the Send ARP Request option if needed to get information to complete the frame. The router then transmits the data. Notice that this last step uses direct routing because the two devices are on the same network. The data finally arrives at the destination PC. The PC unwraps the data, layer by layer, until it reaches the actual data. Now let's return to our discussion about longest match routing. Earlier, we used the postal analogy to describe how a letter gets to its final destination. We learned that during the routing process, post offices use more and more of the postal code to make a routing decision as the letter gets closer to its final destination. The same is true of IP routing. Let's see this process in action using Acme Company's new manufacturing location. Remember that the manufacturing location was assigned the 192.168.3.0/24 address range, which was then divided into several subnets. Let's say that PC 192.168.1.5 needs to send data to PC 192.168.3.36. When the packet arrives at router A, the router performs a longest match route lookup and sends the packet to router B. Notice that router A's routing table does not contain the different subnet numbers actually in use at the manufacturing location. In fact, router A doesn't even need to know that the 192.168.3.0/24 address range was subnetted. Instead, it simply has the address range allocated to that location or a summary route. Route summarization, or route aggregation, combines a group of network numbers into a single route. Route aggregation makes routing traffic across the network and the internet much more efficient, as there are fewer routes in the routing table and fewer routes to advertise. As a packet gets closer to its destination, the routing table entries get more specific, much as the post office uses more of the postal code the closer a letter gets to its destination. This way, routers don't have to keep track of every destination network or route in its routing table, which would slow down routing significantly. Routers always use the longest match available to forward traffic. In this example, the destination IP address is 192.168.3.36. Although the first and fourth routing entries both match this destination, the router uses the fourth entry to forward the packet because it is the longest match. Host 192.168.3.36 is on the network 192.168.3.32. It might not be so obvious why the first routing table entry matches the destination. Once again, it's much clearer if we view this example in binary and compare the network portion of each address. Our destination address matches the routing table entry number 1 with a 16-bit prefix length. Notice that 192.168.0.0/16 represents the address range 192.168.0.0 through 192.168.255.255. And while the destination does fall in this range, the router will try to find a better match using more bits. This address range, which is an example of a Cider supernet, is actually the combination of many other address ranges that are located at corporate headquarters, such as 192.168.1.0/24, or other locations that the manufacturing location doesn't even know or need to know about, such as 192.168.5.0 or 192.168.10.0. Supernetting alleviates some of the issues with the original IP addressing scheme by allowing multiple networks' address ranges to be combined, either to create a single larger network or just for route aggregation to keep the internet routing table, or any routing table, from growing too large. We can see that the destination address does not match entry number 2, which has a 30-bit prefix length. Several bits in the network portion of this address do not match. Nor does it match entry number 3, because the last bit of the network portion of the address does not match. However, it does match entry number 4, with a 27-bit prefix length. It does not match entry number 5 because the last 2 bits do not match. Out of the 2 matches we found, entry number 4 is the longest, most specific match for our destination address. Finally, before we leave the subject of IP addressing, let's take a look at one of the challenges that packets face when they traverse different types of networks. IP's main responsibility is to deliver packets between devices. Remember that a Layer 3 or IP packet is encapsulated in a Layer 2 frame. But before a packet can be encapsulated in a Layer 2 frame, a device needs to make sure that the packet is small enough to fit into that Layer 2's frame size. As we've seen, different Layer 2 technologies have different frame formats. Each data link technology, such as Ethernet or FDDI, has a fixed upper limit on the size of a packet that can be sent in a single frame. This limit is known as the Maximum Transmission Unit, or MTU. Different data link technologies have different MTU sizes. So what happens when a router receives an IP packet that is larger than the next Layer 2 MTU? That's where another responsibility of IP comes into play. IP was designed to accommodate these differences through a process called fragmentation. If a packet is bigger than the MTU of the Layer 2 technology, a device might need to break the packet into several pieces or fragments. The fragments are then sent individually and reassembled into the original packet by the receiving device. When host A begins generating packets, it checks the MTU for its local network, which in this case is 1500. As the packet crosses routers, each router checks the MTU for the next network in the path. If the network has a smaller MTU than the current packet size, the router fragments the packet into smaller pieces. Each fragment contains an IP header that duplicates most of the original header, followed by as much data as can be carried to keep the total length smaller than the network's MTU. The fragments are now sent as separate packets until they reach the destination, where they are reassembled by host B. At this point, we now know how IP addressing and subnet masking work. We learned about the different fields in an IP header, and we've seen how an IP datagram travels from a source device to a destination device using Ethernet as our Layer 2 networking technology. In our next section, we'll examine several wide area network, or WAN technologies, and see how they differ from Ethernet.